Welcome back to week 6 of pre-calculus. Our last topic this week is exponential functions. Remember, we talked a little bit about exponential functions when we talked about linear functions. Linear functions have the distinctive property that they grow or decay by a constant additive per unit of time. In the table below, g, which is 2x, is a linear function. By contrast, an exponential function is one in which growth or decay occurs by a constant multiplicative factor per unit of time. Compare the function 2x with the function 2 to the power x. So let us play a little bit more with this table. So what can we say about this function g, which we know is linear? The distinctive feature again is that if I compute the difference of the value of g at time x plus 1, if I view x as time, and the value of g at time x for any x, that should be constant, independent of x. In fact, we know it's going to be slope, and slope is 2. And indeed, I can confirm this by a simple computation. G at x plus 1 is 2 times x plus 1, and g at x is 2x. When I do the computation, that's going to be 2. The important thing here is that the difference doesn't depend on x. So from here, I immediately see that g at time x plus 1 is g at time x plus 2. So the value of g grows by 2 every unit of time. That is the case for any linear function. Linear function g of x equals 2x grows by 2, which is slope, units, every unit of time, every hour, for instance. And indeed, we can see that in the values of g in the table. Within 1 hour, we grow by 2. Within the next hour, we again grow by 2. Within the next hour, we again grow by 2, and so on. Within every hour, we grow by 2 units. If you ask the same question about the function f, you can see immediately that it's not true that f grows, and indeed it grows, by the same amount every unit of time. Within 1 hour, f grows by 1. Within the next hour, f grows by 2. Within the next hour, f grows by 4. Within the next hour, f grows by 8, and so on. In fact, the distinctive feature of the exponential function, as we will see, is that the ratio of the values of an exponential function at 2 consecutive times is constant. What I mean by this is that if I were to compute f at time x plus 1 and divide it by f at x, that will be constant, independent of x. And indeed, f at time x plus 1 is 2 to the power x plus 1, and f at time x is 2 to the power x. Simple algebra shows that 2 to the power x plus 1 is 2 to the x times 2, and 2 to the x cancel, so we end up with 2. From here, it follows immediately that f at x plus 1 equals 2 times f at x. So the value of f doubles every unit of time. The value of f right now is twice what it was 1 unit of time ago. Do not confuse linear and exponential functions. They're completely different. G grows by 2 units every unit of time. You add a 2 every unit of time. F grows by a factor of 2 every unit of time. So every unit of time you multiply by 2. As you can see, the growth of f is much faster than that of g. Both are increasing functions, but f grows much, much faster than g. In fact, exponential function, if it grows faster than any polynomial function. When you take calculus, you will prove this fact properly. But meanwhile, I wanted to mention the fact that you are actually very well familiar with exponential functions because they naturally arise, especially in banking. When, for instance, you invest $1,000 at a given annual percentage rate, an annual percentage rate is this factor by which you multiply every unit of time. Annual means every year. Abbreviated as APR, of say 8%. The price P of the portfolio as a function of time. We will explain in a minute, right now, that P of t is an exponential function. But let's play a little bit with this situation. You start with $1,000. How much are you going to have in your portfolio in 1 year? Well, in 1 year, you're going to have what you had before, 1,000, plus that times 8%. And if you factor out 1,000, that's 1,000 times, in parentheses, 1 plus 0.08, which is simply 1,000 times 1.08. How about in 2 years? In 2 years, you're going to have what you had in the beginning of year 2, which is 1,000 times 1.08, plus that 1,000 times 1.08, times 8%. And if we again factor out this common factor, 1000 times 1.08, in parentheses we have 1 plus 0.08, and this is 1000 times 1.08 times again 1.08, because the expression in parentheses is 1.08. So overall we have 1000 times 1.08 squared. Continue this in 3 years. You're going to have what you had at the end of year 2, which is 1000 times 1.08 squared plus that same amount times 8%. Factor out 1000 times 1.08 squared. In parentheses, we're going to have 1 plus 0.08. When you do the algebra, you end up with 1000 times 1.08 cubed, because again, the expression in parentheses is 1.08 times 1.08 squared results in 1.08 cubed. We have here a very clear pattern, and so the price of portfolio P as a function of T is simply 1000 times 1.08 to the power T, where T is measured in years. T is measured in years. And indeed, this is an exponential function, because if I were to compute the ratio of the values of P at time t plus 1 and at time t, I would have 1000 times 1.08 to the power t plus 1 over 1000 times 1.08 to the power t, and of course 1000 and 1000 cancel out. In the numerator, I can write 1.08 to the power t plus 1 as 1.08 to the power t times 1.08 again, so the 1.08 to the power t in the numerator and the denominator cancels, and I end up with 1.08. So this already implies that p of t is an exponential function. It has this distinctive feature, the ratio of two values at any given moment of time, and at that moment of time plus 1 is constant. P of t is an exponential function. And if you write P of t as, rather P of t plus 1 as 1.08 P of t, and then you break 1.08 as 1 plus 0.08, you see that P at time t plus 1 is P at t plus 0.08 P of t. And that really shows how this function works. So at the end of the next year, you get back what you invested plus what you invested times the 8%. All right, I think now we are ready for a formal definition. By an exponential function, we will mean a function of the form a times b to the power x. Now there are three symbols here, a, b, and x. A and b are given constants. The actual variable is x. A is necessarily non-zero. If a were zero, the whole thing would be zero, and this would be a constant function. B, the base of this expression, the base of this power, is necessarily positive, because if b were negative, you would have problems when you raise that number b to negative powers. There is no way to unambiguously define the power of a negative number unless that power is a natural number. So a is non-zero, b is positive, and we also require that b be not equal to 1, because if b is 1, we again get a constant function. For the function f, in this table, a is 1, the factor in front of the power, and b is 2. In the example that I gave on the left, a is 1000 and b is 1.08. So what I was saying before about the ratio of values of an exponential function being constant simply translates to the fact that if we assume that our constant factor a is positive, then for b greater than 1, the function grows at a rate proportional to itself. And if b is between 0 and 1, the function decays at a rate proportional to itself. But in our theory, let's look at the graphs of exponential functions, specifically at the graphs of 2 to the power x and 2 to the power negative x, which is of course the same as 1/2 to the power x. The pictures are on the next page. So 2 to the power x has a very distinctive look. It's an increasing function that passes through the point 0, 1. That's because 2 to the power 0 is 1. To the right of 0, it grows extremely fast. The graph pretty much becomes vertical very quickly. Vertical, of course, in quotation marks. And likewise, to the left of 0, the graph decays also very rapidly. And moreover, y equals 0 is a horizontal asymptote. Which is to say that the limit of 2 to the power x as x goes to negative infinity is 0. So the graph of the function becomes arbitrarily close to the x-axis without ever intersecting with the axis. The function is defined for all x, so the domain is the entire real line. It only assumes positive real numbers as values, and any such positive real value is taken. Any positive real number is taken as a value. So the image of the function 2 to the power x is the entire set of positive real numbers. Now, what can we say about the function 1/2 to the power x, which is, of course, the same as 2 to the negative x? Well, if you recall one of the previous topics, transformations of functions, when you replace x by negative x, that corresponds to reflecting the graph about the vertical axis, about the y-axis. So the graph of 1/2 to the power x may be obtained by reflecting the graph of 2 to the power x about the y-axis. And so it still passes through the point 0, 1, because that point is on the axis. It now decays everywhere very rapidly. The x-axis, the straight line with equation y equals 0, is still a horizontal asymptote. The function is still defined on the entire real line. And the image is still the entire set of positive real numbers. We can summarize all these observations in a theorem. Suppose we have an exponential function where, again, a is non-zero, b is positive and different from 1. The function is a times b to the power x. The domain of the function is always the entire real line. The image depends on the sign of a. Remember, a is non-zero. Whenever a is positive, like in the two examples on the next page, the image is the entire set of positive real numbers. And when a is negative, the image will be the entire set of negative real numbers. Let's actually draw an example with a negative. Let's say we have a function negative 1 times 1/3 to the power x. How would the graph of that look like? Well, the graph of 1/3 to the power x would look very similar to the graph of 1/2 to the power x. So it's an ever decreasing curve passing through the point 0, 1 and rapidly approaching its horizontal asymptote y equals 0. As we know from that topic about transformation of functions, placing a minus in front of the function has the effect of flipping the graph over the horizontal axis. So the graph of negative 1/3 to the power x would look like this. It would be an ever increasing function passing through the point 0, -1, and the horizontal axis y equals 0 would still be its horizontal asymptote. And you can see that what we said before about the image is indeed true. The image of this function is the entire set of negative real numbers, the interval from -infinity to 0. That's clear from the picture. Any exponential function has the horizontal axis as a horizontal asymptote, regardless of the sign of a, for b greater than 1. A limit at negative infinity is 0, which implies that y equals 0 is a horizontal asymptote. And for b squeezed between 1 and 0, the limit at positive infinity is 0, which means again that y equals 0 is a horizontal asymptote. The sign of a and whether b is less than 1 or greater than 1 determines whether our function will be decreasing or increasing. For positive a and b greater than 1, our exponential function is increasing, like 2 to the power x. If a is positive but b is between 0 and 1, like in the case 1/2 to the power x, our function is decreasing or decaying. For a less than 0, the conclusions are vice versa. If a is negative and the base is greater than 1, you can think of, say, negative 2 to the power x, the function is decreasing. And if a is negative and the base is between 0 and 1, like in this example here, negative 1/3 to the power x, where a is negative 1 and b is 1/3, we clearly see that the function is increasing. All right, let's look at some more examples. In this example, we're told that the population of India in the year 2013 was 1.25 billion people. And it's known that the annual growth rate is 1.2%. There are two questions. First is write down the function governing the growth of the population. And the second question is, what will be India's population in the year 2031? All right, let's introduce some notation. Let's say capital P is population. It's always a good idea to keep track of what units you are using. Looks like we are measuring population in billion people. And let time be denoted by t. Looks like time is measured in years, but not since the birth of Christ, as we normally do, as we normally measure time, but rather since the year 2013. So the year 2013 corresponds to t0. Therefore, t is time passed since the year 2013, measured in years. So given that, we see immediately that the function governing the growth of the population is simply p of t equals 1.25 times, what should it be? 1 plus 1.2%, correct? That is 1 plus 0.012. 0.012, that's 1.2%. So when I add the two numbers, I get 1.012. That is the base of my exponential function. That's b. Now, what about the second question? What will be India's population in the year 2031? Unfortunately, some students make this mistake here and say that p at the year 2031 is simply that formula where instead of t, I write 2031. If you actually do that, you will obtain that the population of India in the year 2031 will be 4 times 10 to the power 10, but not 10 to the power 10 people. 10 to the power 10 is 10 billion. It might be possible for India to house 10 to the power 10 people, but we are measuring population not in people, but in billion people. So it will be 4 times 10 to the power 10 billion, meaning billions of people. And definitely that goes against common sense. The entire planet won't be able to house that many people. So of course you see that the mistake is that we agreed to measure time since the year 2013, and therefore instead of replacing t by 2031, I should replace t by the number of years passed since the year 2013. So that is a mistake. And the correct way to compute the population of India at the year 2031 would be to replace t in the exponent by whatever the years passed since 2013. 2031 minus 2013, that is 18. The difference between 2031 and 2013. So I should raise 1.012 to the power 18, and that will be approximately 1.55 billion people. So the population of India in the year 2031 is projected to be roughly 1.5 billion. Right now it is, or in the year 2013 it was 1.25 billion. So it'll increase by roughly 250 million people. So when you write this formula, it won't hurt to remind yourself that here t is the number of years passed since 2013. So you don't fall into that trap and don't make that mistake. All right. In the next example, we have a wolf population, and it's known that the population is growing exponentially. Also, we know that in the year 2011, we had 129 wolves. By 2013, the population had reached 236 wolves. What 2 points can be used to derive an exponential equation model in this situation? And write the equation representing the population n of wolves over time t. Again, it is very important to keep in mind that we already know that the population grows exponentially. So let us again introduce some notation. Let's say t is time in years, and let's measure time since 2011. It will be convenient. So in particular, 2011, that is t equals 0. And 2013, that is t equals 2. 2 years after 2011. Now, the population n of wolves is an exponential function, so we can write n, rather we look for capital N in the form n of t equals a to the power a times b to the power t, where a and b are to be found. What information can we use to find a and b? We can use the fact that n at 0, 0 means 2011, is 129. The other piece of information that we can use is that n at 2, 2 is 2013, is 236. So what can we do with this information? Well, n at 0, being 121, on the other hand, is a times b to the power 0. That is a times 1, that is a. And that is 129. So we find immediately that a equals 129. On the other hand, n at 2 equals a times b to the power 2, and that's 236. A we know is 129, so 129 times b squared equals 236. From here, b squared is 236 over 129, and then b is plus minus square root 236 over 129. Now, should we take a positive square root or a negative square root? Of course, we take the positive square root because remember the base of an exponential function has to be positive and different from 1. So we take the positive square root. B is positive square root 236 over 129. And therefore, n of t, the population of wolves as a function of time, is a, which is 129, times b, which is square root of 236 over 129, to the power t. Here, 129 is a, and square root of 236 over 129 is b. You can see that this number b, square root of 236 over 129, is greater than 1, and this exponential function will be growing. The population of wolves grows. The next example is very similar. Given 2 points with coordinates 1, 3, and 2 and 4.5, find the equation of the exponential function that passes through these 2 points. Once you know that your function is exponential, 2 points is enough to reconstruct the function completely. If we look for that function in the form a times b to the power x, where a is positive, a is non-zero, I apologize. B is positive and different from 1. We are told that f at 1 is 3 and that f at 2 is 4.5. On the other hand, f at 1 is a times b to the power 1, which is just ab, and f at 2 is a times b to the power 2, ab squared, and that's 4.5. If I now divide one of these equations, ab squared equals 4.5 and ab equaling 3, I will get that ab squared divided by ab equals 4.5 divided by 3. But ab squared divided by ab is simply b. And 4.5 divided by 3 is 1.5. So I immediately get that b equals 1.5. And now once I know b, I can use the first equation, ab equals 3, to find a. So a is 3 divided by b, which is 3 divided by 1.5. And so a equals 2, excuse me. 3 divided by 1.5 is 2. So now we know that f is simply 2 times 1.5 times x. By the way, this function f, because the base is 1.5, models a growth by 50% every unit of time. If x measures time in years, for instance, this would be annual growth of 50%. You invest $2,000 or just $2, and annually, every year, your investment portfolio grows by 50%. All right, let's take a break here. We'll be back soon. Thank you.